Picture an environment, literally more hostile than deep space. A realm of absolute, pitch-black darkness, where the crushing weight of the environment itself actively wants to tear apart anything that dares to enter it. To survive down there, humanity didn't just build a ship, right? We had to build an entirely enclosed, self-sustaining world. Welcome to this explainer. Today we're dissecting what is arguably humanity's most complex engineering marvel, the submarine. We're going to strip away the steel and titanium to reveal exactly how these massive underwater leviathans operate as the invisible fortresses of our oceans.
Naval engineers and military strategists really describe them best when they say, submarines are today among the most complex engineering products humanity has developed, the invisible fortresses of the ocean. And if you think about it, it makes total sense. A modern submarine has to perfectly marry aerospace-level tolerances with advanced nuclear energy, intricate acoustics, fluid hydrodynamics, and now even artificial intelligence. It's an absolute masterclass in extreme engineering.
Okay, here's our blueprint for today. We've got 1. Primitive to nuclear giants. 2. The physics of the deep. 3. Surviving the pressure. 4. Sonar and acoustic stealth. 5. Power and survival. And finally, 6. The autonomous future. Let's dive right in.
Section 1. From primitive to nuclear giants. To really appreciate where we are today, we have to look at the staggering leap in this technology. Back in 1620, Cornelius Drebbel actually built a working submarine using a wooden hull covered in greased leather. Can you imagine? By 1775, we had the single-person turtle deployed in the American Revolutionary War. Then, a major, though pretty grim milestone hit in 1864 when the H.L. Hunley became the first sub to actually sink an enemy warship. Fast forward to the 1900s, and the diesel-electric era kicked off the modern submarine age. But today, we have totally left diesel in the dust. We're in the era of nuclear giants like the Virginia and Bory classes. These vessels operate on just an entirely different scale of power.
Section 2. The physics of the deep.
So how exactly do you take a vessel weighing thousands of tons and make it gracefully glide up and down through the water column? Well, it all comes down to mastering buoyancy, specifically Archimedes' principle. This principle states that a submerged object experiences an upward buoyant force equal to the weight of the water it displaces. For a submarine, this is everything. By precisely manipulating its weight to match the exact weight of the water it displaces, a sub achieves what's called neutral buoyancy. It doesn't sink, it doesn't float, it simply hovers, perfectly suspended in the water down to the exact centimeter.
And this mastery over buoyancy happens through the ballast system. When a sub is on the surface, its ballast tanks are filled with air, which gives it positive buoyancy. When it's time to dive, valves open up and dense seawater just rushes into those tanks. The submarine's overall weight goes up, its density surpasses the surrounding water, and down it goes. To rise back up, high-pressure air is blasted back into those tanks, violently forcing the seawater out, lightening the sub, and bringing it right back to the surface. It is just a beautifully brutal application of basic physics.
Section 3. Surviving the crushing pressure. Now, as that submarine dives deeper, it meets the single greatest enemy of deep-sea engineering, oceanic water pressure. And this is a terrifying reality. For every 10 meters a submarine descends, the pressure goes up by 1 atmosphere. If you go down to a depth of 1,000 meters, the pressure is a staggering 101 atmospheres. To put that into perspective, that means the pressure hull, the literal tube where the crew lives and breathes, is enduring roughly 1,000 tons of force per square meter. The ocean is literally trying to crumple the submarine like a tin can.
To survive that kind of squeeze, engineers have to be incredibly strategic about materials. Historically, the US has relied on high-yield steels like HY80 and HY100. These offer incredible yield strength to resist collapsing, but Soviet engineers, they took a totally different route, pioneering the use of titanium, which you might know from the famous Alpha-class submarines. Titanium is fascinating. It's incredibly strong, way lighter than steel, highly resistant to saltwater corrosion, and it has a very low magnetic signature, so it's harder to detect. The catch? It is agonizingly expensive and notoriously difficult to weld together.
Section 4. Sonar and acoustic stealth.
Once you survive the pressure, your next problem is navigating an environment where light basically doesn't exist. Submarines have no eyes. They see by analyzing sound waves. It's a massive, high-stakes acoustic game of cat and mouse using sonar. You've got 2 main tactics. Passive sonar is like cupping your hand to your ear. The submarine goes completely silent and just listens for acoustic signatures like an enemy's propeller.
Active sonar is completely different. It's like shining a massive flashlight in a dark forest. You send out a powerful acoustic ping and listen for the echo. You'll get a precise location of your target for sure, but the huge downside is that everyone else in the ocean now knows exactly where you are too.
But here's the thing, sound underwater behaves super weirdly. Its speed and trajectory actually change based on temperature, salinity, and pressure. A really masterful submarine commander will use something called the thermocline layer. This is a zone where the ocean temperature suddenly drops. Because sound travels differently through different temperatures, this layer actually refracts or bends sonar waves. So a sub will dive beneath the thermocline and effectively use that thermal barrier as a cloaking device to hide from surface sonars. It's brilliant!
And to survive this acoustic combat space, modern engineers literally designed the submarine to be a virtual silence machine. They use anechoic rubber tiles that completely cover the outer hull. These act like acoustic sponges, absorbing incoming active sonar pings instead of bouncing them back. Also, instead of traditional propellers, many modern subs use pump jet systems. This drastically reduces cavitation, which is the incredibly noisy popping of water bubbles made by fast-spinning blades. And inside, they use raft vibration isolation. The massive engines are mounted on springs and rubber platforms, so their vibrations never actually touch the outer hull.
Section 5. Nuclear power and survival.
Let's step inside that pressure hull for a second. You have an entirely enclosed ecosystem in there. Keeping a crew alive and powering a massive warship for months without servicing requires an unbelievable power source. We're talking 20 to 30 years. Modern nuclear submarines use these incredibly sophisticated pressurized water reactors. By fissioning highly enriched uranium, they generate immense heat, turning water to steam to drive the turbines. The sheer endurance is mind-blowing. A modern naval reactor gives you limitless power and propulsion for decades without ever needing a refuel. And that limitless power is exactly what keeps a crew of 100 to 180 people alive under extreme isolation. I mean, to breathe, they literally extract air from the ocean. They run an electrical current through seawater, a process called electrolysis, to separate the H2O and synthesize breathable oxygen. Then, they use chemical scrubbers to constantly pull deadly carbon dioxide out of the air. Need a drink? The reactor powers reverse osmosis systems that purifies seawater into totally fresh drinking water. Really, the only limiting factor on a modern nuclear sub's mission is just how much food they can physically stuff into the pantry. This unparalleled endurance brings us to the SSBNs, nuclear-powered ballistic missile submarines. Because they have this limitless power and can stay hidden in the deep ocean indefinitely, they are the most survivable leg of the nuclear triad. They carry intercontinental ballistic missiles, like the Trident II, that can travel thousands of kilometers. They truly are the ultimate, unseen foundation of global strategic deterrence.
Section 6. The autonomous submarine future. So, the nuclear giants of today are incredible, but the engineering doesn't stop here. The depths are gearing up for a radical evolution. We're shifting from heavily crewed leviathans to highly intelligent, silent machines. Artificial intelligence is already stepping into the acoustic space, analyzing massive oceans of sonar data in milliseconds to find the faintest enemy signatures. But looking ahead, we're moving toward completely unmanned autonomous systems. Imagine fleets of uncrewed drone subs mapping the ocean floor. Engineers are even working on super silent magnetic propulsion, with literally zero moving parts, and quantum navigation systems that could let submarines maintain pinpoint accuracy for months without ever needing a GPS signal.
We've journeyed all the way from greased leather barrels in the 1600s to today's titanium-hulled nuclear leviathans. And right now, we are standing on the brink of an AI-driven underwater revolution. The technology is advancing faster than ever, and it's slowly stripping away the ocean's remaining shadows. It leaves us with a pretty intense question to think about. With artificial intelligence and autonomous systems silently mapping the deepest, darkest trenches on the planet, who really controls the unseen fortresses of tomorrow's oceans? Thanks for joining me on this explainer, and I hope this deep dive completely changed the way you view the waters covering our world.